Hi, welcome back to my class in Advanced Statistics. For today, we will take up the probability distributions for continuous random variables. In basic statistics or elementary statistics or statistics 1, we have taken that there are two types of data, the qualitative data and the quantitative data. And the quantitative data are classified into two as discrete data and continuous data. Discrete data refer to data that can be obtained by counting. And the discrete data are the values that are taken by discrete random variables whose probability distributions we have already taken. And for today, we will start with the probability distributions of continuous random variables. A continuous variable is a variable that whose values represent data that are continuous data, which means that continuous random variables represents take values that are continuous data. And continuous data are data that are obtained by measurements. And so examples of continuous random variables are variables that represent the lengths, the heights, and weights of people, the length of time it takes a person to complete a task or a job, the time between service calls for a machine or equipment, and the waiting time if you are waiting for a bus in a bus station. And there are three types of probability distributions for continuous random variables. The simplest of which is the uniform probability distribution for a uniform random variable. The second is the exponential probability distribution for exponential random variable, and the last one is the normal probability distribution for normal random variable. But the normal probability distribution we have already taken in basic statistics or statistics 1. And so for our course in advanced statistics, we will take just the first two probability distributions for continuous random variables, and today we will start with uniform probability distribution. But before that, to differentiate the probability distribution for discrete random variable and the probability distribution for continuous random variable, we know that in a probability distribution for discrete random variable, for each value of the discrete random variable, there is a corresponding probability. And the number of values that a discrete random variable can take is finite and countable. That is, there is the first and last value for the discrete random variable if that random variable is represented by x. And the other property of the probability distribution for discrete random variable is that the sum of the probabilities corresponding to the possible values of the random variable is equal to 1. Now, the approach in probability distribution for continuous random variable is through the use of relative frequency. The relative frequency that is associated with an interval or class is the fraction or proportion of the population that fall in that class or interval. And we take an example. Suppose the random variable x takes a value and any values between the points A and B on a line interval. In probability distribution for continuous random variable, the if we are considering this line interval between the points A and B, this is a line interval because these A and B are real numbers. These are points on the real line. And it is an interval because we have a lower limit and upper limit. And a random variable, a continuous random variable can take infinitely many values between these points A and B on this line interval. Unlike in the discrete random variable, x can only take a finite number of values between A and B. And usually those are real numbers, whole real numbers, and countable. But in continuous random variable can take infinitely many values between A and B, as many as there are real numbers between A and B. Now, the relative frequency associated with this line interval between A and B is the fraction of the measurements, or the proportion of the measurements in the population that fall between A and B. Thus, the fraction of the measurements in the population that fall in the line interval between A and B. And that fraction represents also the probability that a random variable, a continuous random variable x value will fall between A and B, or will lie in the line interval between A and B. And that's the main difference between the probability distribution for discrete random variable and the probability distribution for a continuous random variable. And the first of the three probability distributions for continuous random variable, as I said, is the uniform probability distribution. In the uniform probability distribution, the value of the random variable x can take any value or values between the points A and B on a line interval. This rectangle represents the shape of a uniform probability distribution. And the probability that x will fall between these points A and B in this line interval is equal to the area of this rectangle. And the area of the rectangle is given by the product of the length and the width. And the length here is the difference between B and A, or the length of this rectangle is B minus A. While the width of this rectangle corresponds to the height of the rectangle. And the height of the rectangle can be obtained by calculating the area of this rectangle. As in the probability distribution for discrete random variable, the total area of this rectangle should be equal to 1. Now, applying the formula for the area of rectangle, which should be equal to 1, we find the height or the width of this rectangle. The area of rectangle from your elementary geometry is equal to the length times the width. And the the sum of the probabilities for probability distribution for continuous random variables should be equal to 1, similar to the probability distribution for discrete random variable. The length, as we have shown in this diagram, is equal to b minus a. The length of this rectangle is b minus a multiplied by the width is equal to 1. And dividing both sides by b minus a, we get w is equal to 1 over b minus a. We divide the left hand side by b minus a, and b minus a in the numerator we cancel out with b minus a in the denominator, and we also divide the right hand side 1 by b minus a. Therefore, w, the width of the rectangle, which corresponds to the height of the rectangle, is 1 over b minus a. This means that for any value of x between a and b on this line interval, the height, the corresponding value of f of x represents the relative frequency, is equal to 1 over b minus a. This function f of x equals 1 over b minus a is called the probability distribution, or more specifically, the probability density function for the uniform probability distribution for continuous random variable, where x is between a and b. Again, this function f of x equals 1 over b minus a, which is a constant. That means for any value of x between a and b, the value of the function f of x is always 1 over b minus a. And the function f of x is called the probability distribution, or more specifically, the probability density function for the continuous random variable x. And you can see from the diagram that for any value of x between a and b, the value of f of x is always 1 over b minus a. And for values of x between the endpoints a and b, the part of the graph of f of x is this horizontal line from this point up to this point. And we can now check that the total area of this rectangle is 1. The length is b minus a multiplied by the width, which corresponds to the height of the rectangle, 1 over b minus a, and we get 1. Now the mean of this, the mean of the values of x for the uniform probability distribution for continuous random variable is denoted by mu, and it is the midpoint of this line interval between a and b. And to get the midpoint, we simply add the endpoints a and b and divide by 2. This value a plus b is halfway between a and b. It is the midpoint of the line segment between a and b. And the standard deviation of the continuous random variable x, denoted by sigma, is directly proportional to the length of this line interval. And it is given by the following formula. Again, the standard deviation, sigma, of the values of the continuous random variable x per uniform probability distribution is directly proportional to the length of the line interval between A and B. The length of this line interval is B minus A. And the constant of proportionality is 1 over square root of 12. Now we take some examples for applying this formula to problems involving uniform probability distribution. For our first example, consider the following problem. Buses arrive at a bus stop every 15 minutes, and the waiting time for the next bus to arrive has a uniform probability distribution on the interval from 0 to 15 minutes. Letter A, find the probability that a person's waiting time will exceed 10 minutes. Letter B, calculate the mean and standard deviation for the continuous random variable for this example. And also for letter B, graph the probability density function and indicate the location of the mean and the endpoints of the intervals mu plus or minus sigma and mu plus or minus 2 sigma. And letter C, find the containment probabilities for the two intervals in letter B. In this problem, the buses at a given bus stop arrive every 15 minutes. Therefore, the waiting time of a person who wants to catch a bus in this particular bus stop will be between 0 and 15 minutes. 0 if the person arrives at the point that the bus arrives, and so the person will not have to wait for the bus if that person arrives at exactly the time when the bus arrives. But if the person misses the bus, then the longest time that person will have to wait for the next bus is 15 minutes, because the buses arrive in this particular bus stop every 15 minutes. And the problem says that the waiting time for the next bus to arrive is described by uniform probability distribution, which means that the shape, when we graph the probability density function for this example, will be rectangular in shape. In letter A, we want to find the probability that the person will have to wait for the next bus for more than 10 minutes. In letter B, we calculate the mean and the standard deviation for the continuous random variable for this example. And we also grab the probability density function f of x for letter B. And in that same graph, we plot the endpoints of this interval, mu plus or minus sigma. This interval has a lower limit of mu minus sigma and an upper limit of mu plus sigma. Also in the same graph, we plot the endpoints of this interval, mu plus or minus 2 sigma, which means that the lower limit of this interval is mu minus 2 sigma, and the upper limit is mu plus 2 sigma. Let us see, find the containment probabilities for the two intervals. The containment probability means, refer to the probability that the waiting time of a person who wants to catch a bus will fall in this interval mu, in the interval between mu minus sigma and mu plus sigma. And we also find the probability that the waiting time, the time that a person will have to wait for the next bus, will fall in the interval between mu minus 2 sigma and mu plus 2 sigma. And that is what is meant by containment probabilities. So we start now. To start up, we first represent the waiting time by a variable, which we take as x. We let x be the waiting time of a person who wants to catch a bus for the next bus. We let x be the waiting time of a person who wants to catch a bus. And the possible values of x here will be between 0 and 15 minutes. And x will have infinitely many possible values because there are infinitely many numbers between 0 and 15 minutes. So x here represents a continuous random variable. And in letter A, we want to find the probability that a person's waiting time will exceed 10 minutes. It will exceed 10 minutes if x is greater than 10. To simplify, we now partly sketch the graph of this uniform probability distribution for this example. In the vertical axis, you write f of x. F of x represents the probability density function. In the horizontal axis, you write x, the continuous random variable x, which can take any values between 0 and 15 minutes. And we want to find the probability in letter A that the waiting time x will exceed 10 minutes. That means the value of x will be greater than 10. So we locate x is 10 in the horizontal axis. I have used a 5-minute intervals for the horizontal axis. This is 0, 5, and 10. Now we find the value of the density function f of x when x is 10 and when x is 15. And from our discussion earlier, the probability density function for uniform probability distribution f of x is given by 1 over b minus a. Where in this example, the values of x are between 0 and 15 minutes. This means that A is 0 and B is 15 minutes. Hence, f of x simplifies to 1 over b 15 minus a 0. Or this is 1 over 15. This means that for any value of x, the value of the density function f of x is always a constant 1 over 15. When x is 0, the value of the density function f of x is 1 over 50. And if we sketch the graph of this function f of x over, which is equal to 1 over 15, it will be a horizontal line parallel with the x-axis. For any value of x between 0 and 15, the value of f of x is 1 over 15. When x is 0, f of 0 is 1 over 15. When x is 10, the value of f of 10 is 1 over 15. So the height of this rectangle from 10 to 15 is 1 over 15. And the length of this rectangle is 15 minus 10 is 5. Now, the probability that the waiting time of a person will exceed 10 minutes or will be greater than 10 minutes, that means from this point up to 15, is equal to the area of this rectangle with length of 5 units and height of 1 over 15. Again, the probability that the waiting time x of a person will be more than 10 minutes is equal to the area of this rectangle with length with this side from 10 to 15 or a length of 5 units and this height of 1 over 15. So we calculate this probability that x greater than 10 minutes by getting the area of this rectangle, and the area of a rectangle is equal to the length times the width, where the width corresponds to the height of this rectangle. The probability that the waiting time of the person is greater than 10 minutes will exceed 10 minutes is equal to the area of this rectangle, this shaded rectangle. Area of the rectangle is equal to the length times the width, where the length is 5 and the width is equal to the height of the rectangle, 1 over 15. And 5 multiplied by 1 is 5, divided by 15, that's 5 over 15, and we reduce it to lowest terms, we get 1 over 3. Hence, the probability that the waiting time of a person will exceed 10 minutes or will be greater than 10 minutes is 1 over 3 or 1/3, or that's 33.33%. For letter B, we now calculate the mean and the standard deviation of our continuous random variable x representing the waiting time. As I said earlier, the mean denoted by mu of the continuous random variable x for uniform probability distribution is the midpoint of the line interval between A and B. In our example, A is 0 and B is 15 minutes. Hence, the mean of the continuous random variable x representing waiting time of a person for the next bus to arrive is 7.5 minutes. A is 0 plus B 15 all over 2. 0 plus 15 is 15 divided by 2 is 7.5 minutes. On the average, a person who wants to catch a bus on that particular bus stop will have to wait 7.5, 7.5 minutes on the average. Now, we also calculate the standard deviation for our continuous random variable x denoted by sigma. As I said earlier, sigma, the standard deviation for the continuous random variable x for a continuous uniform random variable is directly proportional to the length of the interval, the line interval between A and B, where the constant of proportionality is 1 over square root of 12. And the length of the interval from A to B is given by B minus A. In our example, A is 0 and B is 15. Therefore, the length of this interval from 0 to 15 is 15 minus 0 or 15 minutes. And we calculate this value, the value of 15 over square root of 12 to 2 decimal places using our calculator. We have 15 divided by square root of 12. And to 2 decimal places, you should get 4.33 minutes. In letter B, we are asked to sketch the graph of the probability density function f of x. And in letter A, we have defined the probability density function for this particular example as follows. Our probability density function for this example is f of x is given by 1 over b minus a, where b is 15 and a is 0. So 1 over b minus a is 1 over 15. The value of the function, the probability density function f of x is always a constant 1 over 15 for any value of x between the points 0 and 15 minutes. And this is the graph of the probability density function f of x equals 1 over 15 for values of x between 0 and 15. In the vertical axis, you locate 1 over 15, and from that point, you draw a horizontal line parallel with the x-axis up to the point x equals 15. When x is 0, the value of the probability density function f of x is 1 over 15. When x is 15, the value of the probability density function, or this height, is 1 over 15. For any value of x between 0 and 15 minutes, the value of f of x is always 1 over 15. And this is the graph of the probability density function f of x equals 1 over 15 for values of x between 0 and 15. In letter B, we are also asked to locate the endpoints of the intervals mu plus or minus sigma and mu plus or minus 2 sigma. The first interval is the interval mu plus or minus sigma with lower limit, lower endpoint of mu minus sigma, and upper limit or upper endpoint of mu plus sigma. And we substitute the mean 7.5 minus sigma, the standard deviation 4.33. For the upper limit or the upper endpoint, we also substitute mu 7.5 plus sigma 4.33. And we calculate this difference and this sum using our calculator. We have 7.5 minus 4.33 and we use 2 decimal places. We get 3.17. And we find the sum 7.5 plus 4.33. And we get 11.83. We are also asked in letter B to locate to plot the mean, and the mean is the midpoint of the line interval from 0 to 15. Now we plot the endpoints 3.17 and 11.83 on the horizontal axis. And this is 5 units, this is 10 and 15. We approximate 3.17. We plot 11.83. Now we also calculate the endpoints of the interval mu plus or minus 2 sigma. The interval mu plus or minus 2 sigma has lower limit or lower endpoint of mu minus 2 sigma and an upper limit or upper endpoint of mu plus 2 sigma. We substitute the value of mean mu 7.5 and the value of standard deviation sigma equals 4.33. And we compute this value 7.5 minus twice of 4.33 using our calculator. We have 7.5 minus 2 times 4.33. And you should get negative 1.16. We also calculate the sum of 7.5 plus twice of 4.33. and that's 16.16. And we plot these endpoints on the horizontal axis. Because this is negative, this point is to the left of 0. And 16.16 is after 15, that is to the right of 15. For letter C, we calculate the containment probabilities for these intervals mu plus or minus sigma and the interval mu plus or minus 2 sigma. Which means that we find the probability that the waiting time of a person waiting for the next bus will fall between 3.17 minutes and 11.83 minutes. We also find the probability that the waiting time of a person waiting for the next bus will fall between negative 1.16 and 16.16. We now find the probability that the waiting time of a person waiting for the next bus to arrive will be between 3.17 minutes and 11.83 minutes. And as we have shown earlier, the probability that the waiting time of the person waiting for the next bus to arrive will be between 3.17 minutes and 11.83 minutes is equal to the area of the rectangle bounded by the vertical line from passing through 3.17 and the vertical line passing through 11.83. And the rectangle is also bounded by the line interval from 3.17 to 11.83. And this upper part of the graph of the probability density function f of x. So this probability is equal to the area of the rectangle from 3.17 to 11.83. And the area of the rectangle is equal to length multiplied by the width, where the width in this example corresponds to the height of the rectangle. The length is equal to the length of the interval from 3.17 to 11.83, which is equal to 11.83 minus 3.17. And the width of the rectangle, the vertical line through 3.17 or the vertical line through 11.83 is equal to the height of the rectangle, which is 1 over 15. We compute this difference and we divide by 15 and we take the final answer to 2 decimal places. We have 11.83 minus 3.17. The difference is 8.66 and we divide that by 15. Again, we compute 11.83 minus 3.17. We get 8.66. We divide by 15. And to two decimal places, that's 0.58. Rounded off to two decimal places, we get 0.58. And so the probability that the waiting time of a person waiting for the next bus to arrive in that particular bus stop will be between 3.17 minutes and 11.83 minutes is 0.58, or multiply that by 100%, we have 58% the probability that the waiting time of the person waiting for the next bus to arrive will be between 3.17 minutes and 11.83 minutes. The next part of letter C, we find the probability that the waiting time of the person waiting for the next bus to arrive will be between negative 1.16 and 16.16. And we now know that this probability that the waiting time x of the person waiting for the next bus to arrive will be between negative 1.16 and 16.16 minutes is equal to the area of the rectangle bounded by the vertical line through negative 1.16 with a height of 1 over 15, and this the part of the horizontal axis from negative 1.16 to positive 16.16, also bounded by this vertical line through 16.16 with a height of 1 over 15. And the upper boundary is the horizontal line from negative 1.16 to 16.16. The area of the rectangle, as we know, is equal to the length multiplied by the width. And the length of the interval from negative 1.16 to 16.16 is the difference between 16.16 and negative 1.16. This is the length of the rectangle multiplied by the width, and the width is equal to the height of this rectangle, 1 over 15. Again, we calculate this difference, but this becomes a sum because negative times negative is positive. Hence, we compute 16.16 plus 1.16, and the sum we divide by 15, and we round off the final answer to two decimal places. 6.16 plus 1.16 and we divide by 15. The answer is 1.15466 is repeated. If we round this up to whole number, the answer would be 1. We round it up to whole number because if we take the answer as to two decimal places, we would get 1.15, and we know that the maximum probability value is 1 or 100%. So we round this answer to whole number when we get 1 or 100%. The probability that the waiting time of a person waiting for the next bus to arrive will be between negative 1.16 and 16.16 minutes is 100%. And it should be 1 or 100% because this line interval from negative 1.16 to 16.16 already contains the maximum waiting time for any person waiting for the next bus to arrive, which is 15 minutes, and the lowest waiting time possible is 0. Therefore, the probability that the waiting time of the person waiting for the next bus to arrive will be between negative 1.16 and 16.16 is 1 or 100%. And that completes the solution for our first example. We now take another example. Our next example, consider the following problem. A random variable x has a uniform probability distribution with density function given as f of x equals 1 for x greater than equal to 0 and less than equal to 1. Letter A, graph the probability distribution for x. B, find the probability that x falls between 0.5 and 0.75. And letter C, calculate the mean and variance of x. Based from the given information, we know that x is a continuous random variable because its values can be any number between 0 and 1. And we know that there are infinitely many real numbers, in particular decimal numbers between 0 and 1. And the density function for the continuous random variable x, f of x is equal to 1, which is equal to 1 over b minus a, where b is 1 and a is 0. So if you make use of that formula, f of x equals 1 over b minus a, you will get 1 over 1 minus 0, or 1 over 1, which is 1. Letter A, we graph the probability distribution for x. In the vertical axis, we write the frequency, relative frequency defined by the density probability density function f of x. In the horizontal axis, we write the line interval that where x can have any value. In the given, we have the line interval from 0 to 1. And the value of the probability density function f of x is equal to 1 for any value of x between 0 and 1. So we construct the rectangle from 0 with height of 1 unit. And from this point, we draw a horizontal line parallel with the x-axis up to x equals 1. And that is the graph of the probability distribution for the continuous random variable x. And you must check that the total area of this rectangle must be 1. By formula, area of the rectangle is length multiplied by the width. The length is the length of the interval from 0 to 1, which is equal to 1 minus 0, 1. And the width is equal to the height of the rectangle, 1. So length times width is 1 times 1, 1. And this is for letter A. For letter B, find the probability that x falls between 0.5 and 0.75. plot this line interval from 0.5 to 0.75. And we construct the rectangle from 0.5 when x is 0.5, f of x is 1. When x is 0.75, f of x is 1. And the probability that the value of the continuous random variable x will be between 0.5 and 0.75 is equal to the area of this rectangle. And the area of the rectangle is equal to length multiplied by the width, where the length is equal to the length of the line interval from 0.5 to 0.75 and is equal to 0.75 minus 0.5. Multiplied by the width. The width is equal to the height of this rectangle, which is equal to 1 unit. And we get 0.75 minus 0.5 is equal to 0.25. Multiplied by 1, we get 0.25. Hence, the probability that the value of the continuous random variable x will fall between 0.5 and 0.75 is 0.25 or 25%. And letter C, we calculate the mean and variance of the random variable x, the uniform random variable x. The mean, as we have said earlier, is equal to the midpoint of the line interval from 0 to 1, and the midpoint of the interval from A to B is equal to the sum of the endpoints divided by 2. Where A is 0 and B is equal to 1. Hence, the average value of the random variable x is 0.5. A is 0 plus B is 1. 0 plus 1 is 1. Divided by 2 is 0.5. The value of the uniform random variable x on the average is 0.5. And the standard deviation sigma is given by the difference between the length of the line interval from 0 to 1 and divide by the square root, the positive root of 12. But the required in letter C is the variance. This is the standard deviation sigma. It's directly proportional to the length of the interval from A to B. And the variance is equal to the square of the standard deviation. Therefore, we take the square of both sides. The square of sigma is sigma square is equal to the square of B minus A over square root of 12. And we apply one of the properties of exponents. The square of B minus A over square root of 12 is equal to the square of B minus A divide by the square of 12. Now we substitute the values of a and b in the given interval from 0 to 1. A is 0 and b is 1. So this becomes 1 minus 0 squared. And by property of exponent again, the square root of 12 is equal to 12 raised to 1 half. And 1 half multiplied by 2 is 1. Therefore, the square root of 12 is 12. One minus 0 is 1, and 1 is square is 1. Divide by 12. Therefore, the variance of the uniform random variable x is 1 over 12. And that completes the solution of our example 2. For your practice, please try the following exercises. Number 1, the amount of time a person is required to wait for an elevator in a large department store is uniformly distributed with a range of waiting time from no wait, that is 0 seconds, to 3 minutes and 30 seconds. If customers wait for more than 2 minutes and 45 seconds, they develop negative impressions of the commitment of the store to customer service. Using the department store's elevator, what is the probability that customers will develop negative impressions of the store's commitment to customer service? Commitment to customer service. In number 1, the random variable x is the waiting time, the amount of time needed to wait for the elevator in a large department store. And the waiting time is between 0, that is, there is no need to wait, and 3 minutes and 30 seconds. I suggest that you convert the time, all the time, to seconds. So 3 minutes and 30 seconds would be 180 plus 30, that's 210 seconds. And there was a study that showed that if customers wait for more than 2 minutes and 45 seconds, that's 205 seconds. 2 minutes is 120. 2 minutes is 120 seconds plus 45, that's 165 seconds. A study showed that if customers wait for more than 2 minutes and 45 seconds or 165 seconds, they develop negative impressions of the commitment of the store to customer service. And the problem is asking for the probability that the customers in that department store will develop negative impressions of the commitment of the store to customer service. And to solve that, you will use the information given about the waiting time for an elevator in that department store. Number 2, a random variable x has a uniform probability distribution with density function given as f of x equals 1 half for x between 2.5 and 4.5. Letter A, graph the probability distribution of x. And B, find the probability that x will fall within the interval mu plus or minus k sigma for k equals 1, 2, 3. In letter B, you should have 3 answers. First, for each of the 3 answers, you have to first calculate the mean mu and the standard deviation sigma. And then you start with k equals 1. You compute the lower and upper limits or lower and upper endpoints of the interval for k equals 1, or the interval mu plus or minus sigma. And then you find the probability that the value of the random variable x will fall between mu minus sigma and mu plus sigma. And then you take k equals 2, you compute the lower and the upper endpoints or limits of the interval mu plus or minus 2 sigma, and you find the probability that x, the value of x, will fall within that interval. And the third value of k is 3. You compute the limits or endpoints of the interval mu plus or minus 3 sigma, and then you also find the probability that the value of x will fall in that interval from mu minus 3 sigma to mu plus 3 sigma. And that completes our lesson for today on the first type of probability distribution for continuous random variable, the uniform probability distribution for uniform random variable. If you have questions about the lesson today, you ask your question in the comments below. And in the next lesson, we will take the second type of probability distribution for continuous random variable, called the exponential probability distribution for exponential random variable. Thank you for joining me in my class today in Advanced Statistics.